Learning objectives. At the end of this topic, you will be able to analyze figures on the same base and between the same parallels, prove parallelograms on the same base and between the same parallels, prove parallelograms on the same base that have equal areas and lie between the same parallels. Prove that two triangles on the same base and between the same parallels are equal in area. Introduction. In geometry, two figures or objects are congruent if they have the same shape and size. Observe the figures A and B. If you superimpose figure B over figure A, such that it will cover figure A completely, so if two figures A and B are congruent, they must have equal areas. However, the converse of the statement is not true. In other words, two figures having equal areas need not be congruent. Consider the figures rectangle and square. In both the figures, the area is equal, but they are not congruent. Consider another figure. You may observe that planar region formed by figure T is made up of two planar regions formed by figures P and Q. From this, you can easily say that area of figure T is equal to the area of P plus area of Q. Area of a figure is a number associated with the part of the plane enclosed by the figure with the following two properties. If A and B are two congruent figures, then area of A is equal to area of B. And if a planar region formed by a figure T is made up of two non-overlapping planar regions formed by figures P and Q, then area of T is equal to area of P plus area of Q. In this lesson, we will study some relationship between the areas of these geometric figures under the condition when they lie on the same base and between the same parallels. Figures on the same base and between the same parallels. Let's look at the figure shown here. In this figure, we have a parallelogram ABCD and a triangle PDC. Both the parallelogram and the triangle lie on the same base DC. Also, the vertices A, B, and P that are opposite to the base BC lie on the line AP. Line AP is parallel to the base DC. Here, these two lines are called parallels. Consider another figure. Here, the trapezium APCD and the parallelogram ABCD are on the same base DC. The vertices A, B, E, and F opposite to the base DC lie on the line AF that's parallel to DC. In both the figures, we have polygons that lie on the common base and the vertices that lie on the line opposite to the base. So, two figures are said to be on the same base and between the same parallels if they have a common base, side, and the vertices or the vertex opposite to the common base of each figure lies on a line parallel to the base. Now look at these figures. Can we say that these figures are on the same base and between the same parallels? No. Though the base is common, the vertices opposite to the base do not lie on the line parallel to the base. Now we'll discuss the parallelogram that are on the same base and between the same parallels. Consider the two parallelograms ABCD and EFGH. Let's rearrange these parallelograms. The parallelograms are now on the same base AB and between the same parallels AB and CH. Can you find if there is a relationship between the areas of these two parallelograms? We know that the area of the parallelogram is the product of the base and the height. Yes. In the figure, the base of both the parallelograms is AB. We'll name it as small b. Since both the parallelograms lie between the same parallels, the height of the parallelograms are equal. We'll name the height small h. The bases and height of both the parallelograms are equal. Does it imply area of both the parallelograms are equal? Let's see. Yes, it does. Area of parallelogram ABCD is equal to area of parallelogram EFGH. Here, let's prove the theorem. Parallelograms on the same base and between the same parallels are equal in area. In the parallelogram, ABCD and EFCD are on the same base DC and between the same parallels AF and DC. We need to prove that area of parallelogram ABCD is equal to the area of parallelogram EFCD. When the two parallelograms lie on the same base, two triangles ADE and BCF are formed. In triangle ADE and triangle BCF, angle DAE is equal to angle CBF. Since AD is parallel to BC, AF is transversal, so the corresponding angles are equal. Denote this as equation 1. Similarly, ED is parallel to FC. Again, AF is transversal, so angle AED is equal to angle BFC. Denote this as equation 2. Therefore, by angle sum property of a triangle, angle ADE is equal to angle BCF. Denote this as equation 3. Also, AD is equal to BC. This is because AD and BC are the opposite sides of the parallelogram ABCD. Denote this as equation 4. Using equation 1, 2, and 3, by SAS rule, we can say that triangle ADE is congruent to triangle BCF. We know that congruent figures have equal areas. Therefore, area of triangle ADE is equal to area of triangle BCF. Now, area of parallelogram ABCD is equal to the area of triangle ADE plus area of quadrilateral EBCD. Using equation 5, area of triangle BCF plus area of quadrilateral EBCD. This gives us the area parallelogram EFCD. Hence, the parallelogram ABCD and EFCD are equal in area. Now let's prove the corollary of the theorem we just proved. Corollary states that parallelograms on the same base and having equal areas lie between the same parallels. ABCD and EFCD are two parallelograms on the common base DC. The areas of these parallelograms are also equal. Let's assume the base parallelogram B and heights are H1 and H2 respectively. Applying the formula for area of parallelogram, we can express the equation 1 as follows. Cancelling B, that is common on both sides, we have H1 is equal to H2. As the heights of the parallelograms ABCD and EFCD are equal, the common base DC and opposite side AF are parallel. Thus, the corollary is proved. Remember that all figures that are on the same base and between the same parallels need not have equal areas. Both the figures are on the same base between the same parallels AB and CD. Since ABEF is not a parallelogram, the areas of ABCD and ABEF are not equal. Let's see a few examples based on same base and between the same parallels. Prove that parallelograms on equal bases and between the same parallel are equal in area. Given that ABCD and PQRS are parallelograms, AB is equal to PQ, L is parallel to M. We need to prove that area of parallelogram ABCD is equal to area of parallelogram PQRS. Draw AE perpendicular to DR, PT perpendicular to DR. Let's begin with a proof. Using the formula area of parallelogram ABCD is equal product of base and height, we have area of parallelogram ABCD equal to product of AB and AE. Denote this as equation 1. Similarly, area of parallelogram PQRS is equal to product of PQ and PT. Since AB is equal to PQ, given PT is equal to AE, as perpendicular distance between parallel lines are equal, so the product of PQ and PT can also be written as product of AB and AE. Denote this as equation 2. From equations 1 and 2, we have area of parallelogram ABCD is equal to area of parallelogram PQRS. Consider the next example. In a parallelogram PQRS, PQ is equal to 5 centimeters. Altitude corresponding to PQ and RS are 3 centimeters and 4 centimeters respectively. Find PS. We know that area of parallelogram PQRS is equal to product of base and altitude. Here base is equal to PQ, altitude is ST. Substitute the values of PQ and ST. We get 5 times 3, which is equal to 15 centimeters square. Also, area of parallelogram PQRS is equal to product of PS and QX. Now substitute the value of QX. So we have 4 times PS. From equation 1 and 2, we have 15 is equal to 4 PS. Since LHS of equation 1 and 2 are equal, this gives RHS also equal. On simplifying, we get PS is equal to 3.75 centimeter. Triangles on the same base and between the same parallels. Consider two triangles ABC and PBC on the same base, BC, and the vertices opposite to the base lie on a line that's parallel to the base. What can we say about the areas of these two triangles? Is there a relationship between the areas of the two triangles? We know that area of triangle is equal to half the product of its base and the corresponding height. We'll use this formula to see how the areas of two triangles on the same base and between the same parallels are related. The triangles ABC and PBC have a common base BC. Let's name it as small b. The height of triangle ABC is AR with respect to the base BC, and that of triangle PBC is PS with respect to the base BC. Both the triangles are between the same parallels, BC and AP. So their heights are equal. Let's name the height as small h. The area of the triangle ABC is equal to half the product of BC and AR, and the area of triangle PBC is equal to half the product of BC and PS. Let's substitute the base and height of both the triangles. The right-hand side of both the equations are equal. Therefore, the left-hand side of both the equations are also equal. This implies area of triangle ABC is equal to area of triangle PBC. Two triangles on the same base or equal bases and between the same parallels are equal in area. Two triangles ABC and DBC are on the same base BC and between the same parallels EF and BC. We need to prove that area of triangle ABC is equal to area of triangle DBC. Through B, draw BE parallel to AC, intersecting line AD at E, and through C, draw CF parallel to BD, intersecting the line DA at F. Let's begin the proof. EACB and DFCB are parallelograms, since two pairs of opposite sides are parallel. Also, parallelogram EACB and parallelogram DFCB are on the same base BC and between the same parallels EF and BC. Therefore, area of parallelogram EACB is equal to area of parallelogram DFCB. Denote this as equation 1. Now, AB is the diagonal of parallelogram EACB. Area of triangle EAB is equal to area of triangle ABC. Area of triangle ABC is equal to half of area of parallelogram EACB. Denote this as equation 2. Similarly, area of triangle DBC is equal to half of area of parallelogram of DFCB. Denote this as equation 3. From equations 1, 2, and 3, we get the area of triangle ABC is equal to area of triangle DBC. Thus, the theorem is proved. The converse of this theorem is also true. The converse states that two triangles having the same base or equal bases and equal areas lie between the same parallels. This implies if triangle ABC and triangle ABD lie on the same base AB and the areas are equal, then B is parallel to CD. Here we'll see some examples of triangle on the same base and between the same parallels. Given, let ABC be a triangle. AD is the median of the triangle. We need to prove that area of triangle ABD is equal to area of triangle ACD. Draw AL perpendicular to BC. Since AD is the median, so BD is equal to DC. Area of triangle ABD is equal to half the product of its base BD and altitude AL. By using equation 1, we have half the product of DC and AL. This is equal to area of triangle ACD. Therefore, area of triangle ABD is equal to area of triangle ACD. ABCD is a quadrilateral. A line through D parallel to AC meets BC produced at P. Prove area of triangle ABP is equal to area of quadrilateral ABCD. Given, let ABCD be a quadrilateral, DP is parallel to AC. We need to prove that area of triangle ABP is equal to area of quadrilateral ABCD. Triangle ACP and triangle ACD are on the same base AC and between the same parallels AC and DP. This implies area of triangle ACP is equal to area of triangle ACD. Adding areas of triangle ABC on both sides, we get area of triangle ABC plus area of triangle ACP is equal to area of triangle ABC plus area of triangle ACD. This implies area of triangle ABP is equal to area of quadrilateral ABCD. Summary. Let's summarize the topic. Two figures or objects are congruent if they have the same shape and size. Two figures having equal areas need not be congruent. Area of a figure is a number in some unit associated with a part of the plane enclosed by the figure with the following two properties. If A and B are two congruent figures, then area of A is equal to area of B. And if a planar region formed by a figure T is made up of two non-overlapping planar regions formed by figures P and Q, then area of T is equal to area of P plus area of Q. Two figures are said to be on the same base and between the same parallels if they have a common base, side and the vertices, or the vertex opposite to the common base of each figure lies on a line parallel to the base. Parallelograms on the same base or equal bases and between the same parallels are equal in area. Area of a parallelogram is the product of its base and the corresponding altitude.